Let me welcome you to this lecture by Steve Redding, who've met a couple of times before, I think, and he's going to talk about quantitative urban models.
Thanks very much, Fabienne and Daniel. Thanks very much to the organizers for the invitation to participate in this great initiative. I think it's a really exciting time in urban economics with new GIS data coming online, new theoretical frameworks being developed. And that was very evident at the last Urban Economics Association meeting, just in terms of the high quality of research and also just how young and diverse the set of researchers are. And so this is a really exciting time in the urban field. What I wanted to do today is talk about quantitative urban models and place them in the context of some of the earlier material covered in previous lectures. So if you think about urban economics in general, the complexity of modeling spatial interactions between agents means that traditionally, the urban literature, from a theoretical point of view, has focused on highly stylized settings. So for example, we saw in Ed's lecture, the classic monocentric city model. In other contexts in economic geography, it's frequent in theoretical settings to assume a small number of symmetric locations. And while those are important in terms of clarifying mechanisms and distilling insights from this class of economic models, obviously, it's very hard to directly connect such stylized models with real-world data. And so that sort of inspired a more recent wave of research, which has tried to develop quantitative urban models, which are rich enough to capture first-order features of the data, such as, for example, many locations that we typically have in data sets that might have heterogeneous productivity and amenities, and might be connected by a rich transport network. And so these models are designed to sort of directly connect with the objects that we see in the data. On the other hand, they typically try to preserve a relatively small number of structural parameters that is feasible to estimate using variation in the data, using natural experiments. And also at the same time, despite the richness of these models, the idea is that they remain sufficiently tractable that we can actually use them to undertake realistic policy counterfactuals. So for example, we might think of a real world scenario where a policymaker wants to build a new subway line from location A to location B, and we can directly use the model to simulate a counterfactual for what the impact of that policy intervention would be on the spatial organization of economic activity. And so what I'm going to talk about today is I'm going to focus on a set of quantitative urban models that are designed to look at the organization of internal economic activity within cities. But of course, these are part of a wider body of research on quantitative trade and spatial models on which many of you are working. And so in particular, what I'm going to abstract from today is I'm going to abstract from models of systems of cities. So I'm really kind of focusing on a single city, thinking about how economic activity organizes within that city. And then more generally, of course, this single city will be in a system of cities, but we're going to abstract from a lot of that today. So just to connect a little bit more back to Ed's lecture and think about where these quantitative urban models connect with the traditional theoretical literatures. As Ed mentioned, the classic theory model for thinking about internal city structure is the so-called Alonzo-Muth-Mills monocentric city model, where obviously all the key assumption is that all employment is concentrated in the center of the business district, in the center of the city, and then workers face commuting costs in commuting to that central employment location. And then building on that traditional literature, there are a couple of path-breaking theoretical contributions that seek to model non-monocentric cities from a theoretical point of view. And so there's a paper by Fujita and Agawa looking at a linear city, and then a paper by Lucas and Rossi Hansberg looking at a symmetric circular city. And I give an example here of the spatial equilibrium in the Lucas and Rossi Hansberg models. This is a really rich model of the organization of economic activity in 2 dimensions and can generate pretty rich patterns of economic activity. So here you see we have alternating rings of commercial and residential economic activity within the city as we move out from the center. So patterns are non-monocentric. We're getting away from the monocentricity assumption of Alonzo-Muth-Mills. And what is driving this? Well, this richness here is driven by the trade-off between agglomeration forces, which means you want to cluster similar activities together, with commuting costs, which means you want to disperse those activities out in different parts of the city to save on commuting costs. Okay, so very, very rich analytical framework. But of course, when we go to the data, the key assumption here that makes the model tractable is that the city is symmetric. And so in the theory model here, the radius of the city perfectly summarizes the organization of patterns of activity. Obviously, as we said, when we go to the data, in reality, real-world cities are going to be asymmetric. And so we're going to try to develop models that can connect with those asymmetries in the data. And so that's what I'm going to try to do today. And so the idea is that this model has to be rich enough to capture what we see in the data. So what is our data going to look like? So the kind of application I'm thinking of is where we have rich data on what I'm going to call employment by workplace, the number of people employed in different locations throughout the city. And so in the Berlin paper I work with later, I'm going to have many thousands of these locations. They're going to be city blocks or census tracts. And so I'm going to see employment by workplace, how many people will work in each of those blocks. I'm also going to see employment by residence, how many people live in each of those blocks. Okay, and so that's the data available in the Berlin application. In the second paper I'm going to talk about later today on London, we actually have even better data. We actually have a matrix of bilateral commuting flows between all of these different locations in the city. And obviously, if we see bilateral flows of people commuting, we can use that to compute employment by workplace and employment by residence. So that's the kind of employment information that we typically think of having available. Key feature of the models I'm going to develop today as well is it's very useful also to have data on land prices. And you saw a hint of why that might be the case in Ed's lecture earlier in the series, that these land prices are going to summarize the overall attractiveness of locations, how desirable they are for both production and residence. And so they're going to be key inputs into the model. And then we're also going to think that we typically observe transport networks. So we might have bilateral shapefiles that show the underground railway lines, the overground railway lines, the roads within a city, and we can use those to compute bilateral travel times between different parts of the city. Or we can use Google Maps to compute bilateral travel times between different parts of the city. And we'd like our model to be rich enough to connect directly to those things that we see in our data set. At the same time, obviously in reality, these locations in the city might have different productivity, different amenities, different supplies of floor space. In other words, the buildings might be different heights, so there might be different ratios of floor space to ground area. And then, clearly, as I mentioned, they're also going to differ in their transport infrastructure. And so the model is going to have to allow for that in order to connect with the data in a realistic way. And then, of course, because we're interested in urban economics and the agglomeration of economic activities within cities, we're typically going to think that there are going to be agglomeration forces inside these models. So as well as allowing for exogenous differences in productivity across locations, some locations might have access to water, which is useful for production. Other locations might not. That's an exogenous difference in productivity. In addition to those, we're also going to want to allow endogenous differences in productivity because of agglomeration forces. So for example, knowledge spillovers between locations and some of the other sources of agglomeration economies that Gilles talked about in his lecture. In the applications I developed today, I'm going to actually allow two types of agglomeration forces on the production side. We're going to have some production externalities where productivity is increasing in the density of employment. And we're also going to allow for some residential externalities where amenities are related to the density of residents. And then like in most theoretical models of cities, the distribution of economic activity is going to be driven by a tension between those agglomeration forces, the differences in exogenous characteristics of locations, and commuting costs. Okay? And so commuting costs, together with an inelastic supply of land, are going to provide the dispersion forces inside the model that are going to work against the agglomeration forces, are going to be the key trade-off inside the model in terms of how much activity concentrates in one place versus disperses to different locations inside the city. And so in the rest of the lecture, I'm mainly going to talk about two different applications. They both do quite different things. And so I thought it was kind of useful to use them to illustrate the kind of things one can do with quantitative urban models. And so the first application looks at the division of Berlin. And so the key idea in that application is to use the exogenous division of Berlin in the aftermath of the Second World War and its reunification following the fall of the Iron Curtain as a natural experiment, a source of exogenous variation to try to structurally estimate the strength of agglomeration and dispersion forces. And we'll see how one might go about doing that within one particular quantitative urban model. And then the second paper I talk about today is called The Making of the Metropolis, Evidence from London. There, the question is connected more directly to a policy intervention that might be up for grabs or might be being contemplated by policymakers. We're sort of interested in thinking about what is the impact of transport improvements on the organization of economic activities within cities. And so that second paper on London actually also makes a couple of methodological contributions, which is why I wanted to kind of highlight it as kind of part of today's lecture. In particular, we're going to develop a framework where we can not only analyze one quantitative urban model, like in the Berlin paper, but we're going to develop a framework that nests an entire class of quantitative urban models. Okay, and so the quantitative approach in the second paper is going to be much more general because it nests an entire class of different quantitative models, and I'll flag some of the advantages of that. Another kind of feature that I wanted to highlight about the London paper is the key difference there from the Berlin paper is in the London data, we have a matrix of bilateral commuting flows between locations within the city. And that's typically commonly the case in many applications with contemporary data. And that availability of the bilateral commuting data is going to allow us to do a lot more things, okay, in terms of understanding the impact of transport improvements on the organization of economic activity. And so we develop a kind of a new structural estimation methodology that leverages that sort of richer data source that we have available to us in the London paper, but we didn't have in the Berlin setting. Okay, and so they're going to form the core of the lecture today. Before I sort of get into those two papers, I just sort of want to flag a sort of third paper, which I'm not going to have time to talk about today, but I think is sort of interesting in terms of the context of today's lecture. That's a paper on goods trade and commuting with Esteban Rossi-Hansberg and Fernando Monte. And the reason I'm flagging that paper here is that everything else I do today, I'm really thinking about a single city, thinking about how economic activity is organized within that city. Whereas in this paper at the bottom here of the slide, we actually have a setting where we can nest that single city in a whole system of cities. Okay, and so if you think about it in terms of the models Ed covered in his lecture, it's combining sort of not just the internal structure of activity within cities like in Alonzo Muth Mills, but it's also bringing in an element of systems of cities, like in Rosen Roback. And so it's trying to bring those two traditions together. Okay, whereas most of what I'm going to concentrate today, I'm going to be thinking about economic activity within a single city. Okay, so without further ado, let's sort of dive into one of these applications and kind of use it as a kind of an example of the types of things one can do with quantitative urban models. So what was the motivation in this paper on Berlin? Okay, well, it was sort of motivated by the sort of big challenge in general in urban economics, which is that when we look at the world around us, we see that economic activity is very unevenly distributed. Okay, we see that in the existence of cities. 19 cities worldwide had a population of more than 10 million already by 2007. But we also see it within cities. If you go to New York or you go to London, you go to other big cities, you'll see that economic functions are often concentrated in particular neighborhoods within cities. So a famous example of the square mile in London, which is the historical financial district. And so a key question in urban economics is understanding why do economic activities concentrate like this? And in particular, the key question is how strong are the agglomeration economies that explain these concentrations of economic activity? And so agglomeration is some form of increasing returns, like knowledge spillovers, as I've discussed. And the dispersion force is typically the scarcity of land and commuting costs, as we also discussed. And so, you know, determining how strong these agglomeration and dispersion forces are is sort of crucial in understanding why cities look like they do. But it's not only of interest for that positive question, it's also of interest for more normative questions or more policy-based questions, such as thinking about what would be the impact of land taxation that varies across different types of locations, transport infrastructure improvements, other types of policy interventions that a policymaker might introduce within a particular city. And so knowing how strong agglomeration and dispersion forces are central to evaluating the effects of those policies. And so that sort of really motivates this first application of quantitative urban models. Okay, but what's the challenge? You know, this question's been around for a long time. Why is it difficult? Okay, well, you know, it's extremely difficult because in the data, we see these activities clustering together, but that could be for one of two very different reasons. On the one hand, the clustering of economic activities could be entirely driven by exogenous differences across locations, by locational fundamentals. So for example, we see very high land values in Hampstead in London. You know, why is that? Well, it could just be that Hampstead's a really attractive place to live. There's a big heath there are scenic views over the city. Maybe it's a very desirable location, and those fundamentals bid up land prices in that location. And so that's one source of reasons why people might want to cluster in one place. It's just it's a great place to be. And in the econometrics literature, that's referred to as correlated individual effects. There are correlated fundamentals that make everybody want to be in this location. On the other hand, why are land prices so high in Hampstead? Well, it could also be because of agglomeration forces. Maybe there are production externalities from bringing highly skilled people together in this neighborhood. Maybe there are residential externalities through, for example, public schools in bringing people with particular levels of education and concentrating them in one neighborhood of a city. Okay, and so working out how much of the high land prices is due to the fundamentals versus how much is due to the agglomeration forces is an extremely difficult identification problem. Okay, and it's a classic problem in the social sciences, distinguishing correlated individual effects from spillovers. And so how have people tried to solve this literature in the past, or this challenge in the past? Well, as Gilles mentioned in his lecture, one approach is to regress productivity on the density of economic activity. And because density is endogenous to productivity, one approach is to instrument density with a plausible instrument that one believes only affects productivity through density. And so a classic example might be bedrock, cities that are built on bedrock. It's easier to build skyscrapers and tall buildings on bedrock. And so that might be a potential instrument for density that plausibly only affects productivity through density. Okay, but it's very, very difficult to find those types of instruments. You know, bedrock is perhaps the exception. It's been very challenging in the literature to find suitable instruments. And furthermore, we don't have a lot of evidence as to what the spatial scale of these agglomeration forces is. How rapidly do they decay in space? And how large are they relative to congestion forces is a sort of another challenge, as again, Gilles discussed. So the key problem here is it's very difficult to find exogenous sources of variation. Exogenous shocks, which are uncorrelated with fundamentals and that move density around, would enable us to estimate the strength of agglomeration forces. And so that's really the motivation for this first application of a quantitative urban model today. It's going to combine a rich model that connects directly with the data in the way we've discussed with an exogenous natural experiment to try to estimate agglomeration forces. What is that natural experiment? Well, it's going to be the division of Berlin in the aftermath of the Second World War, and it is reunification following the fall of the Iron Curtain. And so here the idea is that when Berlin was divided, that changes the density of surrounding economic activity, because in particular, West Berlin loses access to East Berlin and all of surrounding East Germany. And so that's an exogenous shock that was driven by military and strategic considerations. It wasn't driven by particular economic characteristics of different locations within West Berlin. And so it provides an exogenous shock to the surrounding density of economic activity. And so we can use that as a source of variation to try to estimate how does density drive productivity through agglomeration forces. So what I'm going to try to do in terms of discussing this application, I'll say a little bit more about the historical background, why we think this is a sort of exciting natural experiment. And then I'll dive into the particular quantitative urban model used in this paper, try to flag what are its strengths and limitations, how can you use it to try to estimate agglomeration forces. Tell you a little bit about the data. In the published paper, there's actually a big section of reduced form empirical evidence that kind of addresses a variety of concerns you might have. For time reasons, I'm mainly going to skip that during the lecture today, although to focus on the sort of structural estimation of the model, which is going to take up most of my time. Although I would like to flag that often there's a sort of debate in the literature about structural versus reduced form approaches. At least from my personal perspectives, I don't see them at all as being alternatives, but rather as sort of complementary, in the sense that if you find a similar pattern of conclusions with two very different empirical methodologies, that's likely to increase your prior that your findings are robust if you find them with those two different methodologies. Obviously, you know, each one of those methodologies can only do certain things. They're not perfect substitutes for one another, but they each have their advantages and they can kind of reinforce one another. Okay, so what is the historical background here, and why is the division of Berlin a useful natural experiment? Well, the division of the city actually originates in a protocol signed during the Second World War, which organized Germany into American, British, French, and Soviet occupation zones following its eventual anticipated defeat. Although Berlin was around 200 kilometers within the Soviet zone, so in the eastern Soviet zone, 200 kilometers east of the border with the American, British, and French zones, it was sort of decided that as the former capital of pre-war Germany, Berlin itself would be divided into occupation sectors. So how were these sectors chosen? Well, the boundaries between them were chosen to follow the pre-war suburb boundaries in Berlin, which had no particular significance during the pre-war period. And then how did you pick which of these boundaries to use to draw the dividing lines? Well, the idea was to pick those dividing lines such that the different occupation sectors had roughly equal pre-war population between the Soviet, American, and British sectors. And then eventually a French sector was created out of part of the British sector later on during the proceedings. And so this is sort of interesting because this division was not driven by any pre-war economic characteristics. It's really driven by these sort of military considerations of the Second World War and the strategic reason that the Soviet zone should be in the east, where the Soviets were advancing from. The American, British, and later French zone should be in the west, where the Western allies were advancing from. And originally, in fact, the idea was not to divide the city at all. When this protocol was signed, the idea was to have a joint commandatura, a joint committee that would jointly administer the city as a single integrated unit. And it was really only after relations between the Soviets and the Western allies began to break down with the onset of the Cold War. And East and West Germany were founded as separate states, and the border between them was closed. And then paralleling that formation of separate states in East and West Germany, separate city governments emerged for East and West Berlin in 1949. And then following the adoption of Soviet-style central planning in East Germany, all local economic interaction between East and West Berlin comes to a close rapidly. Although for a while, there was no economic interaction between the Soviet sector of Berlin and the Western sectors, for a while, it remained possible to travel from the Soviet sector to the Western sectors. And in particular, that possibility of traveling led to a large outflow of refugees from East Germany through East Berlin to West Germany. And in order to stem that flow of refugees, eventually the East German authorities constructed the Berlin Wall in 1961, which made pretty much all travel, all non-authorized travel from the Eastern zone to the Western zone extremely difficult. And travel from Western sectors of Berlin to the Eastern sector of Berlin was tightly regulated. So this is what that division looked like. So just to give you a sense of the experiment and how we're going to use it in our identification strategy. So here you see the area of pre-war Berlin as defined by its 1920 boundaries, which are pretty extensive. These different blue polygons here are the different pre-war suburbs of Berlin, which had no particular significance in the pre-war period. The red line through the middle here shows you the part of the Berlin Wall that severed West Berlin in the west from East Berlin in the east. And as you can see, this little bit of the Berlin Wall that butts out here, this is the pre-war central business district. For anyone who knows Berlin, that's the area Mitte, right in the center of the pre-war city. And as you can see, the Berlin Wall cuts off West Berlin from the pre-war central business district. So West Berlin loses access to that pre-war concentration of economic activity. And then also, of course, the Berlin Wall also ran all the way around the outer boundary of West Berlin and severed West Berlin from its connections with its surrounding hinterland in East Germany. As you can see from the figure, it's a pretty rich natural experiment. These green lines here are the pre-war underground railways and overground railways. And as you can see, the Berlin Wall cuts off those railway lines at the border. In many cases, the underground railway tunnel was literally bricked up to stop any transit. And so very rich experiment in terms of the transport access effects that it has that we tried to leverage in the reduced form part of the paper. So how are we going to develop a quantitative urban model to understand what is the effect of dividing the city in two and how we can use that experiment to structurally estimate the strength of agglomeration forces? Well, we're going to think of a city being embedded in a larger economy. So that's going to be pre-war Germany before the Second World War, West Germany during the period when Berlin was divided, and then reunified Germany in the period after reunification. And so we're going to think of that wider economy as providing a reservation level of utility U bar. And so individuals are mobile with that wider economy. And so if they live in Berlin, it's going to have to offer them a utility that is equal to that expected utility that is equal to that reservation level of utility in equilibrium. We're going to think in the model of the city of consisting of a set of discrete blocks indexed by I, and they're going to correspond directly to the blocks that we see in the data. As we discussed earlier, these blocks might have buildings of different sizes on them in the real world. And so in terms of the model, we're going to think of that as the blocks having different supplies of floor space. And we're going to denote that supply of floor space by what we call the density of development phi. And so phi is the ratio of floor space to ground area, okay, the density of floor space in a particular location. We're going to take the simplest or sort of quantitative version of the simplest canonical urban model. So on the production side, the structure of the model is going to be very simple. There's going to be a single final good, which is going to be costlessly traded, and it's going to be chosen as our numeraire. So its price is going to be equal to 1 throughout the city. Markets are going to be perfectly competitive, and this final good will be produced with a constant returns to scale production technology. What are we going to think about workers doing in the model, where they're going to choose where to live within the city, a block of residence, where to work within the city, a block of workplace, and they're going to choose how much to consume of the final good and how much floor space to use residentially. And they're going to make those choices to maximize their utility, where, as we said, in equilibrium, their expected utility has to equal the reservation level of utility in the wider economy. Okay, and that indifference condition will endogenously determine the population of the city. How about firms? Well, firms are going to choose where to produce, and they're going to choose inputs of labor and commercial floor space to maximize their profits. And because we've got competitive markets in equilibrium, profits are going to have to be 0 in any location with positive production. Within each of our blocks in the data, we're also going to have to require that floor space is allocated equally, or sorry, not equally, allocated optimally between commercial and residential use. So if we see positive levels of commercial and residential use in a particular block, it has to be the case that owners of floor space are indifferent between using floor space in those two locations. And if we see a block entirely specialized in commercial activity, then the return to using floor space commercially must be strictly greater than the return to using it residentially, and hence there's no residential use in equilibrium. Okay, and similarly, if a block is entirely used for residential use. As we discussed, we want to connect with the data. So we want to allow for the fact that productivity can be different in different parts of the city for exogenous reasons, like some locations have access to water, other locations don't. And we're going to denote those exogenous differences in productivity by little a, and I'm going to call that production fundamentals, the exogenous reasons why some places may be better places to produce than others. And then there are also going to be some endogenous differences in productivity across locations. They're going to come from spillovers in production, from agglomeration forces in production. And I'm going to denote those with this Greek symbol upsilon, which looks like a capital Y. And then similarly, we want to allow for the possibility that some blocks may be more attractive places to live than others. They might have forests and nature nearby, for example. And so we're also going to allow these blocks to differ in terms of their residential fundamentals, little b, exogenous differences in their attractiveness as a place to live. And then again, we're going to allow for the possibility that there are some agglomeration economies in these residential decisions. And I've denoted those here with the Greek letter capital omega. So these are going to be agglomeration forces in residential decisions. And historically, the sort of theoretical literature on urban economics has really been focused on agglomeration forces in production. And so one thing I want to flag here is when we take our model to the data, we find that it's really important in terms of matching the data to allow for externalities in residential decisions. We're not the only people that find that. Several people now have related findings like that. So Rebecca Diamond has a job market paper in the AER, finds something very similar. And so this is sort of a very interesting area where empirically we're sort of finding these endogenous amenities effects, whereas traditionally they haven't figured prominently in theoretical models of cities. And so we're now starting to see a bunch of theoretical papers that are trying to model those endogenous amenities. And I think that's kind of a very interesting area for both theoretical and empirical research. And I'll say more about that later. And then obviously in terms of connecting the model with the data, we're going to assume that workers face commuting costs if they separate where they live and where they work. There's going to be a reason they do that. So it must be because amenities are attractive relative to the cost of living where they live, and they may get a high wage relative to the cost of commuting where they work. Those are the reasons they want to, in equilibrium, separate where they live and where they work. But it's also going to be costly for them to do that. They face costs of commuting between their workplace and their residence. And those commuting costs are going to depend on travel times through the transport network. So the model is going to build in a rich transport network with bilateral travel times between locations. So a few more formal details on the model. I try to sketch out the formal aspects of how it works and then talk through how we estimate it structurally. So we try to keep preference side very, very simple. Cobb-Douglas utility, workers consume some of the final good. Little c is their consumption of the final good. They also consume floor space residentially. Little l is their consumption of residential floor space. And so the utility worker omega gets, who lives in block I. So the first subscript will be where they live, their residence. Works in block J. The second subscript will be their workplace, where they work. And then the omega indicates an individual worker, indexes individual workers. The utility depends on how much they consume of the final good, how much residential floor space they consume. It also depends upon amenities where they live, capital B. And this capital B here is going to include both exogenous and endogenous amenities. I'll talk about how we split them out later. And then the utility is going to depend upon the commuting costs they face, commuting between where they live and where they work. That's going to be dij here. And this is going to be an iceberg commuting cost factor that's going to depend upon travel times. And so we're going to think here of commuting costs being incurred in terms of utility, although you see later that these commuting costs enter the indirect utility function multiplicatively with the wage. And so you could also equivalently think of these commuting costs being incurred in terms of time or in terms of labor. For most purposes in the model, it would be completely isomorphic. Okay, and then the key new element in the model here relative to the traditional theory literature on cities is we're going to allow for the possibility that individual workers might have idiosyncratic reasons for picking a particular residence I and workplace J. And so Zij omega is going to be an idiosyncratic draw that is specific to an individual worker omega and a pair of workplaces J, residences I. Okay, and so this is a very important idea here. What's going to happen is that each worker is going to draw an entire matrix by residence locations, workplace locations. They're the rows and columns of the matrix. And each element in that matrix is a particular bilateral draw for how attractive that pair of residence and workplace is to the worker. And so what is this trying to capture intuitively? Well, it's trying to capture the fact that in reality, there are a whole set of idiosyncratic reasons why you choose to live and work in particular locations. Maybe my mother lives in this neighborhood and I want to live near where my mother lives. That's an idiosyncratic reason I might live in a particular location. Maybe my aunt owns a factory in another location, and so I end up working there because I knew about those employment opportunities through my aunt. Okay, and so it's going to capture all of these idiosyncratic things in reality that mean people make these different decisions. Okay, so if I just use utility maximization and substitute in the equilibrium choices of consumption and residential floor space, we're going to get the standard Cobb-Douglas indirect utility down here, where I can also write utility in terms of the worker's wage, where she works, Wj, the cost of residential floor space where she lives, Qi, and then the price of the consumption good, because that's our numeraire and it's freely traded, its price is 1 everywhere, and so that price has just gone to 1 and disappeared. And then again, in the indirect utility function, we're going to have these amenities, capital B, both exogenous and endogenous amenities, the commuting costs, which here you see are multiplicative with the wage. And then here again, we've got our idiosyncratic preference draw, little z. And then the key to making the whole model tractable is that we're going to follow kind of a long tradition in transport economics and in kind of literature on discrete choice more generally, in assuming that these idiosyncratic preference draws are drawn from an extreme value distribution. Okay, and so in particular, we're going to look at a fresh A version of the extreme value distribution. And so the elements in this matrix are bilateral draws by residence and workplace are drawn independently from this fresh A distribution here. And so the parameter epsilon in the fresh A distribution, which has to be bigger than 1, regulates the dispersion in these idiosyncratic draws. So the larger epsilon, the less dispersion in these draws there is. Okay, and so workers are going to respond more to economic fundamentals rather than idiosyncratic preference draws, because for a higher epsilon, the idiosyncratic preference draws are less dispersed. And then the parameters Ti and Ej, they're scale parameters that are going to control the average draw if for workplaces I, that's the T parameter, and the average draw for residences J, that's the Ej parameter. Those two parameters are going to control the mean idiosyncratic preference draw on average for a workplace and for a residence, respectively. So why do we make that extreme value assumption? Well, it just gives us this beautiful tractable expression. That's the kind of theory reason. It gives us this wonderful expression for the probability that an individual worker chooses to live in block I and work in block J. Okay, it takes this extremely elegant form. It's not just a theoretical reason, it's also an empirical and a quantitative reason. The empirical reason is that this form here implies that commuting probabilities obey a gravity equation, which is a very strong property of the data, real-world data on commuting flows. So that's a desirable feature of the model to have, as it connects very closely with the data. And so what is the intuition for this gravity equation? Well, how many people will commute from residence I to workplace J? Well, that'll depend on how attractive the workplace is, the wage it pays. It'll also depend on how attractive the residence is, how low the price of floor space is Q, how high the amenities in the residence are B, and then how high these preference parameters are that control the idiosyncratic draws. Okay, so how attractive the workplace is, how attractive the residence is, that's going to be very important for the commuting flows. So are obviously the commuting costs between this particular pair, between residence I and residence J. Okay, so it's a commuting flows, constant elasticity function of the commuting costs between I and J. But then also, like in the international trade literature, the flows between I and J don't just depend upon the commuting costs between I and J and the characteristics of workplace J and residence I. They also depend upon bilateral trade costs, bilateral commuting costs between all other possible pairs of residence and workplace, the attractiveness of all other workplaces as measured by their wage, and the attractiveness of all other residences. And so in the trade literature, that's often referred to as multilateral resistance. Bilateral commuting flows don't just depend upon bilateral resistance, bilateral commuting costs, they also depend upon all pairs of commuting costs for all pairs of residence and workplace. Okay. And so if I want to know the total number of people that reside in a particular residence, well, I can just take these commuting probabilities and sum across the workplaces J. Okay, and then similarly, if I want to know the total number of people who work in a particular workplace J, I can just take these commuting probabilities and sum across the residences I. And I get these expressions down here. Furthermore, if I take the probability that you commute between I and J, and I divide by the probability that you live in I, that gives me the conditional commuting probability. What's the probability that you commute from residence I to workplace J, conditional on living in residence I? And that takes this simpler expression down here, where the terms in amenities have cancelled and the terms in residential floor space, price of residential floor space have cancelled in the expression down here. And then here we see another reason why we built the quantitative urban model in this form, why we built in the idiosyncratic heterogeneity, because it implies that if I think about particular workplaces attracting commuters from residences, they face an upward sloping supply function in terms of the wage they offer. And you can see that here in terms of this conditional commuting probability. If I'm in workplace location J and I want to attract more workers from all of these different residences I'm going to have to offer a higher wage to pull in more workers to commute to me. But when I raise my wage, that doesn't give me an infinitely large number of commuters. The elasticity, how many more commuters I attract as I raise the wage, is really driven by this shape parameter epsilon here. Okay, and so we have this constant elasticity, upward sloping supplies of commuters to each location, and that's going to take the model very tractable when we do our structural estimation. Okay, that's why we kind of built that feature into the model. Also, another feature here to flag, in terms of the theory and how we take the model to the data, we're going to think about there being a continuous measure of residence in the city. And so when I look at these probabilities here, they're all continuous measures. They're all in measure space. I've got a continuous measure of residents in each location, a continuous measure of workers in each location. And so there's going to be no idiosyncratic uncertainty in the measure of commuters that each workplace attracts. And so Jonathan Dingle and Felix Tintelnot have a very interesting recent paper where they kind of look at the case where you don't have continuous measures of workers, where you have granularity, and they look at the implications of introducing granularity into these types of models. Okay, so one very important part of this quantitative model in terms of how we took it to the data in Berlin was this conditional commuting probability that we just discussed, and the fact that we've got these upward sloping labor supply functions. Okay, why was that important in our application? Well, one big limitation we faced, that we struggled with in the Berlin paper, is that we didn't see bilateral commuting flows. Later, when we get to the application in London, you'll see we do see those flows, and it enables us to do many more things and to encompass a wider range of models. So because we didn't have that data in Berlin, we had to use the model to help us. So how do we use it? Well, we used the fact that we could see in the data the number of people who work in each location. HMJ, this is workplace employment. And we could see the number of people who reside in each location, HR, okay, again, a measure of people who reside in each location in the model. And then the model tells us that the number of people who work in J has to equal the sum across all locations of the number of people who live in each location times the conditional probability that they commute to J. Furthermore, the model tells us that these conditional commuting probabilities have this functional form here because of our extreme value assumption. And now let's look at this equation here. I observe everything on the left-hand side. I observe residents on the right-hand side. Let's imagine that I can parameterize commuting costs with travel times by assuming they're an exponential function of travel times. Then if I see those travel times, and if I know the parameters, epsilon, the Frechet shape parameter, and kappa, which controls the elasticity of commuting costs to travel times, if I know those two parameters, then I observe everything in this equation apart from wages. Okay, we don't see wages in the data, but given that I observe everything apart from wages, if I know the parameters, I can just use this equation to solve for wages. Okay, and then once I've solved for that vector of wages, it's easy to show that our wage vector has to be unique, conditional on the vector of employment that I observe in the data and the vector of residence that I observe in the data. And so once I then recover those wages, the model is going to tell me all of the bilateral commuting flows. Because once I know wages, I can just tell these conditional commuting probabilities from the formula inside the model. Okay, and so that's a kind of really important part of how we sort of use the model to solve a kind of missing data problem. Okay, now let's see how amenities and productivity play a role in the model in terms of shaping the spatial equilibrium. Okay, then let's start with the amenities side of the model. Well, as we discussed earlier, everyone in the city has to get the same expected utility as the reservation level of utility they obtain in the wider economy. Okay, and that's going to endogenously determine the population of the city. Again, we can use our extreme value assumption to solve inside the model for what expected utility is equal to. And it's equal to this expression down here. It takes a very intuitive form. Expected utility depends upon amenities in every location around the city, wages in every location around the city, the cost of living in every location around the city. And there's a very useful property of the Frechet distribution here, which again is useful taking the model to the data. The Frechet distribution actually implies that the expected utility conditional on picking a particular workplace residence pair is actually the same across all workplace residence pairs in the city. Okay, very surprising property when you first hear it, very unintuitive. It's actually very intuitive. What drives that property with Frechet? Well, let's imagine one particular pair of workplace and residence is much more attractive than any of the others. It offers a higher wage at the workplace and it has better amenities at the residence. You think that would raise utility for that particular pair, and that's true. But what is also going to happen? Well, if this pair is so attractive in terms of its fundamentals, it's going to attract workers who draw worse idiosyncratic draws for that particular pair. And so it's going to attract a worse composition of workers in the sense of workers who have lower idiosyncratic draws for that particular pair. And with the Frechet distribution, that compositional effect exactly offsets the better fundamentals, so that in equilibrium, expected utility conditional on choosing each pair is the same throughout the city. Okay, and then in equilibrium, all of those expected utilities have to be equal to the reservation level of utility in the wider economy. And we can use that property of the model to back out the implied amenities for every location within the city. Okay, again, it's going to be a very simple idea. What are we going to do? We're going to go back to our commuting probabilities. In particular, we're going to look at our residence probabilities, which just sum the bilateral commuting probabilities across all possible workplaces J for a particular residence I. And what do you see in those probabilities? Well, you see there's this nasty looking denominator here, this double summation. And it turns out that that nasty looking denominator is exactly equal to this term here in expected utility. So I can eliminate it. So I can eliminate the nasty denominator and replace it with expected utility. And then I can rewrite those residential probabilities, the measure of people that live in block I relative to the measure of people that live in the city, I've got rid of the nasty denominator, it's U bar here, and I've rearranged the residential probabilities. So on the left-hand side, I've got amenities, capital B, and some other parameters, and there's a common level of utility. And gamma here is just the gamma function for an extreme value distribution. And then on the right-hand side, this is my residential probability, the share of residents that live in this location. And then I've got the price of floor space, how costly it is to live in this location. And then this capital W here is a very interesting idea, captures a very interesting idea in these quantitative urban models. What is it? Well, it depends upon the wage in every employment location, the costs of commuting to those employment locations, and this parameter that controls average taste draws for these workplace locations. So what is this capital W? It's commuting access, the commuting access of this residence to all possible workplaces throughout the city. And so how am I using the model here to back out amenities? Well, I'm backing out a composite of amenities and the common expected level of utility. Only this composite is identified in the model, because if I just scale all amenities by a constant multiple, that's equivalent to just scaling expected utility by a constant multiple, or scaling the reservation level of utility by a constant multiple. So they're not separately identified given the data I have available, but I can identify a composite measure of amenities in each location. So I'm just absorbing all the common parameters into that composite. And then the model says I can back out those composite amenities just from the share of people who choose to live in a location, the price of floor space, which I'm going to see in the data, and commuting market access, which depends upon wages that I solved for earlier. So the idea here is very intuitive. Suppose I see a location which has a lot of people living there, a high share of residents, and has very high prices of floor space, a very high price of residential floor space. What does the model say has to be true about that location? Why are a lot of people choosing to live there, despite it being a really expensive place to live? Well, obviously something else has to be good about the location. And the model tells me the things that have to be good about that location are either its access to employment locations, its commuting market access, or its composite amenities. And so amenities are here backed out as a residual that is everything that's not explained in the data by commuting market access. Okay, everything about the variation in residence and floor prices that's not explained by commuting market access must be due to amenities. And a very interesting property of the model is recursive. I can back out these overall amenities, even if I don't know how much of them comes from the exogenous characteristics of locations, leafy streets and green parks, versus how much comes from agglomeration economies in residential decisions. Okay, later on, I'm going to split out these overall amenities into the exogenous component, little b, and an endogenous component that captures agglomeration forces and depends upon the travel time weighted sum of access to residential densities throughout the city. Okay, so later on, I will break them down, but the model tells me I can determine the overall composite, even if I don't know these parameters that determine this breakdown. Okay, and so that's how agglomeration forces in residential decisions and exogenous differences in amenities enter the model here. What about agglomeration forces in production? Well, that's also going to be a very simple story. Again, we've taken this canonical urban model. We've got a single final good produced in competitive markets with labor and floor space according to a constant returns to scale technology. Again, we're going to assume it's a Cobb-Douglas technology. So output of the final good equals productivity in workplace J, the measure of workers employed in that workplace HM, and the amount of commercial floor space used in that location, which is the total amount of floor space L times by the fraction of that floor space that's used commercially. Okay, and then just like overall amenities had exogenous and endogenous components, overall productivity is going to have an exogenous component, little a. So some locations may be good for production for exogenous reasons, like they have access to natural water. And then overall productivity is also going to have some agglomeration economies, upsilon, and these agglomeration economies depend on the travel time weighted sum of employment density throughout the city, as in the sort of canonical urban model. And again, the model is going to be recursive. You're going to see in a second that we can determine the overall value of productivity in a first step, even before we do this breakdown into its exogenous component and its endogenous component. So even before we know the agglomeration parameters. Okay, so we're going to come straight on to that. So what has to be true in equilibrium in this model? Well, if we have perfect competition and constant returns to scale, we're going to have it be true that the price of the final good is equal to its cost function, its unit cost of production. And so if I just rearrange that cost function, I know that the price of the final good is 1. So I have 1 equals the cost function, rearrange the cost function, and I can express the price of commercial floor space in terms of the wage in each location and the overall value of productivity, capital A. And again, this has a very intuitive interpretation. In the data, I see the price of floor space, Q, and this here little q is the price of commercial floor space. And I saw earlier how I could solve for the wage from the employment data. And so what I'm going to do is I'm just going to use this zero profit condition in the model to back out the value productivity must take in order for production to be profitable in this location, in order for zero profits to be satisfied in this location. So if I see this floor space price in the data, and I see this wage in the data, I know that in equilibrium, firms producing there have to be making zero profits. And under my assumptions about the production technology, that tells me what productivity has to be in order for zero profits to be satisfied. And again, it's recursive. I can determine that productivity, overall productivity, even without knowing how much of it comes from agglomeration forces and how much of it comes from exogenous forces. And then in a later stage, we can split productivity down in the way we discussed on the previous slide. Okay. Okay, and so so far as we've gone through the model, we've seen how to determine amenities, we've seen how to determine productivity. There's another object in the background that we now need to determine, which is the density of development, the ratio of floor space to land area. And the way we're going to do that is use another equilibrium condition of the model. In particular, we're going to use the land market clearing condition of the model. What does the land market clearing condition say? It says that the fraction of floor space that's supplied residentially, so the total supply of floor space L times the fraction that's used residentially, that has to be equal to demand for residential floor space. And I can solve for that in terms of the model, in terms of things that I observe, or I can back out in earlier steps. Similarly, the model tells me that the supply of floor space used commercially, which is the overall supply of floor space times the fraction used commercially, that has to equal the demand for commercial floor space inside the model. And again, using the model's equilibrium conditions, I can solve for that demand for floor space in terms of things I observe, like employment, and things that I've already solved for in earlier steps. Okay, so these give me the demand for floor space, and then on the left-hand side, I've got the supplies of it used residentially and commercially. Okay, so if I add together those two demands for floor space, which are equal to the two supplies for floor space, they have to equal the overall supply of floor space, L. And how is floor space produced inside the model? Well, that's produced, we assume it's produced using a constant returns to scale technology, using geographical land area, K, and a building capital M. Okay, and so obviously in the data, I see geographical land area. That's just the land area of my blocks. And then what I'm going to do is I'm going to use this equilibrium condition to back out what the density of development phi has to be inside the model, where this density of development, under my assumption of a constant returns to scale Cobb-Douglas construction sector, that density of development is just a power function of the supply of building capital. Okay, and so on the left-hand side here, this is the overall supply of floor space. I know it's equal to the overall demand for floor space, which is just the sum of residential demand and commercial demand that I can solve for from objects I've already recovered. And so if I just set these two sides of the equation together, I see land area in the data, and I can back out what the implied supply of floor space must be for there to be in equilibrium. Okay, and so the way to think about this is there's a common structure in a lot of quantitative urban models, is that the exogenous differences in amenities across locations, little b here, are what's called a structural residual. They're allowing the model to exactly fit workers' observed residential decisions. Similarly, the production fundamentals, little a here, are a structural residual. They're allowing the model to exactly fit firms' employment decisions. And then finally, this density of development is a third structural residual. It's allowing the model to be consistent with land market clearing, given the observed geographical land area in each location. And so those ideas are very kind of important in the quantitative urban literature. We want the model to be able to rationalize the data as an equilibrium, and it's those structural residuals that do that inside of the model. So what I'm going to do is I'm going to talk about the model's qualitative predictions for division. I'll briefly show you what happens, and then we're going to take our 10-minute break before we sort of get into the structural estimation of the model. So what does the model say will be the qualitative effect of division? Well, it's going to be very intuitive. We're going to interpret the Berlin Wall as a barrier that cuts off all goods trade between West Berlin and East Germany and East Berlin. It cuts off all commuting, and it cuts off all spillovers of knowledge and production or production agglomeration economies, and it cuts off all externalities in residential decisions, all agglomeration externalities in residential decisions. So what happens when the Berlin Wall goes up? Well, firms in West Berlin cease to benefit from agglomeration externalities in production from employment centers in East Berlin. What's that going to do? It's going to make them less productive, which is going to reduce their demand for floor space. So land prices are going to fall. It's also going to reduce their employment. So employment's going to decline. Firms in West Berlin are also going to lose access to flows of commuters from residential concentrations in East Berlin. So they lose a supply of labor. What's that going to have to happen in equilibrium? Well, we said there's an upward sloping supply function for labor. They're losing one of their sources of supply of labor. So what are they going to have to do? They're going to have to offer a higher wage in order to get commuters from elsewhere. So firms in West Berlin now have to raise the wage they have to pay to attract a given level of employment. And that's also going to reduce the land prices they can afford to pay. It's going to bid land prices down. And it's also going to reduce in equilibrium the amount of workers they employ. So employment's going to fall because wages have gone up. Residents in West Berlin are also going to lose access to employment opportunities in East Berlin. They can't go and work there anymore. And they're going to lose agglomeration externalities and residential decisions. What's that going to do? Well, it's going to reduce their commuting market access and their expected income. And it's going to make it less attractive to live in West Berlin. So it's, again, going to reduce the number of people who live there now. The number of residents is going to fall as it becomes less attractive to live there. And it's going to reduce the land prices they're willing to pay because it's less attractive to live there now because residential externalities have gone down and commuting market access has fallen. So all of these forces are going to lead to a population outflow from West Berlin to the wider economy, as indeed you see during the data. West Berlin shrinks in size in the data. And each of these effects is going to be stronger for the parts of West Berlin that were closer to concentrations of employment and residents in East Berlin. So not only is employment in West Berlin as a whole going to go down, and residents in West Berlin as a whole going to go down, but employment, residents, and land prices are going to fall in the parts of West Berlin that were close to concentrations of employment and residents in East Berlin. And so in equilibrium, what's going to happen is that residents and workers are going to reshuffle across locations and between West Berlin and the wider economy until firms make zero profits in equilibrium in each location with positive production. Workers are indifferent across all locations with positive residents. And again, there's no arbitrage between commercial and residential land use. That owners of floor space can't profitably reallocate floor space between residential and commercial use. Okay, so very intuitive effects of division inside of the model. What do we see in the data? Well, we're just going to look at those predictions qualitatively and then take our break. So what are our data? I mentioned earlier, we see land prices, employment by workplace, employment by residence, and bilateral travel times. We see them for the entire of Berlin in 1936, before the Second World War, and in 2006 after Germany's reunification. And then we observe them for West Berlin in 1986. Everything we do in our quantitative analysis, we're going to focus on the impact in West Berlin. Why is that? Well, West Berlin remained a market economy, and so we'd expect the mechanisms in the model to apply. In contrast, allocations in East Berlin were determined by central planning, which is unlikely to mimic the behavior of the market. We've got pretty rich data at the most disaggregated level. We see these data at the block level, around 9,000 of those in West Berlin, 15,000 of them in Greater Berlin as a whole, West and East Berlin together. Very importantly, and this made the whole project possible, we see land prices. In particular, the Germans have a long history of calculating land prices. And these land prices are calculated for a square meter of undeveloped land in each location throughout the city. For the modern day, they're available electronically by a committee of valuation experts that publishes those valuations. And so if a block's already developed, they publish the land price if it were undeveloped for a representative undeveloped square meter of land. For the historical data before the Second World War, we found them by street or segment of street in Berlin. We had to digitize that, and then we had to allocate tens of thousands of streets to 15,000 blocks in Greater Berlin, which was somewhat of an adventure, as you can imagine. We had to deal carefully with the changes of names, very, very data intensive. But the output of that procedure is that we get, again, a land price for a representative undeveloped meter in one of these blocks. That is the average across the values for these segments of streets that we match to that block. We've also got pretty rich data on the transport network. We have some information on building density we use as an over-identification check on the model. And we got a bunch of other observable characteristics that we can use as empirical controls. So let me just show you what happens to Berlin before we take our break. This is the surface of land prices in 1936 before division. And so these land prices are normalized to have a mean of 1. I'm going to keep that mean of 1 in all subsequent figures. And so height is going to be comparable across each of these subsequent figures. So the higher the peak here, the higher the land price on this particular block inside Berlin. And related to our earlier discussion of Alonzo Muth-Mills, you can see that Berlin was pretty much a monocentric city before division. There's a clear peak of land values here. And this peak is in the area Mitte, just east of the Berlin Wall, when it's subsequently built later. And then it's approximately monocentric, so you can see a sequence of concentric rings of progressively lower land prices around that central business district. One of those peaks around the central business district is an area called the Kurfürstendamm, which was developed into a fashionable shopping district in the period before the Second World War. This gap in the sequence of concentric rings is the Tiergarten Park. For those of you who know Berlin, that's a big area of open space in Berlin. Okay, so approximately monocentric with these concentric rings of lower land values prior to the Second World War. I'm now going to show you the same figure, still in 1936, but I'm just going to show you the part of the city that subsequently in the future became part of West Berlin, just to give you a sense of what the activity was like in East Berlin before the war compared to West Berlin before the war. Okay, so here's the part of Greater Berlin that was in what became West Berlin later in time. And so as you can see here, the pre-war central business district was in the east, and there were 2 parts of these concentric rings that were in West Berlin before the Second World War. One of them is that area around the Kurfürstendamm that I talked about. The other is this other peak here, is the area surrounding the Anhalter Bahnhof station, which was just west of the pre-war central business district and was an area of dense office and commercial development before the Second World War on the edge of the pre-war district. Now I'm going to roll forward in time to the division period. So in 1988, in the middle of the Cold War, or towards the end of the Cold War, when West Berlin has been divided. And the question we're interested in is, what does the land price surface look like in around 40 years' time at the end of the period of division? And so as you can see here, one of those areas of high land prices has been entirely eliminated by the division of the city. And you can see that West Berlin's new central business district during the period of division concentrates around the other peak in the pre-war land prices in the parts of the city that ended up in West Berlin. This is that area around the Kurfürstendamm, and you can see some Western consolidation of that area of high land prices. Now we're going to see what happens when the city is reunified. In 2006, you see we get this resurgence of Mitte as an area of high land prices. So the area that was the pre-war central business district starts to come back as a peak of land prices following reunification. And then you also see, just apparent in this figure here, this part of West Berlin that was on the edge of the pre-war central business district around the Anhalter Bahnhof station also starts to re-emerge as an area of high land prices. And you see that even more clearly if we just focus on the parts of West Berlin in 2006 that were in what used to be West Berlin. Again, you see very, very clearly this resurgence in high land prices in the parts of West Berlin that were close to the pre-war central business district. So very, very consistent with the qualitative predictions of the model. When you cut the city in half, it's the parts of West Berlin that were closest to the pre-war concentrations of economic activity in the east that suffer the most in terms of seeing the fall in their land prices. And then the final thing I'll say just before I stop is that another thing you see from these maps is you see that we find very little treatment effect of the Berlin Wall on the other parts of West Berlin. Okay, land prices don't move at all. You can't see it. It's barely visible in the figure. That's also true in regressions. It's barely discernible in regressions. And so any kind of negative effect of the Berlin Wall on land prices, it's not a kind of a disamenity effect or a fear effect of being right next to the Berlin Wall, because the Berlin Wall doesn't really matter much, except at the parts of West Berlin that used to have good access to the central business district. In those parts of West Berlin, there is a very big treatment effect, consistent with the economic mechanisms in the model. And in the paper, there's a whole big reduced form section of the paper which shows that those findings are robust to throwing everything into regression. We have available wide range of controls, very robust and very quantitatively large. But I mentioned earlier, I'm going to kind of skip all the reduced form part for reasons of time. So I'm going to take a break now, take the 10-minute break, and then we'll kind of wrap up the structural estimation after the break. Thanks very much, Fabian. I think I hand back to you now, don't I, to take some questions.
Steve, are you all right to just answer a few questions before we take a short break?
Sorry, Claire, I forgot you were doing the question, sorry.
No, that's fine. There's many questions in the box. We will just ask a few in the interest of time, but we're fortunate to have Daniel, who may be able to help out with some of them with written responses in the second part. But, taking these in order of the upvotes, a lot of people have upvoted a question here, which is whether the idea of strategic considerations might imply that the placement of the division wasn't fully exogenous, and how we can think about testing this.
Yeah, it's a great question. So that's something we thought about carefully and looked in a lot of detail in the paper. You know, there are actually a couple of fascinating articles that discussed the political negotiations that led to the division. And so in fact, there were a whole set of slightly different permutations of the sectors in the city that involved the Western Allies being in the West and the Soviets in the East. And really the difference between those permutations, there was no particular pre-war characteristic that was sort of salient there. And related to that, one thing we do in the paper is that we have the land price data I've just been showing in these figures. We have it not only in 1936, but also in 1926. So you can do a whole set of placebo tests where we sort of see whether this part of West Berlin that was just west of the former pre-war central business district looked different in terms of its trend growth rates between 28 and 36. And so we don't see any evidence of pre-trends in those earlier data. So sort of two parts to answer the question. First part is that, you know, in the historical literature, there was no real big difference between these different parts of the city. And that's reflected in the fact that during the negotiations, they weren't even sure how they were going to divide the city. There was a whole, you know, there's a whole set of dictates about it, and it was mainly just driven by the Soviets being in the East and the areas having roughly equal population, but you can do that in a couple of different ways, and it wasn't at all clear which way it was going to go. So there's no, you know, historical reason to believe that there were strategic differences. And then furthermore, when you actually look in the data, you don't see any evidence of pre-trends anyway. And so, you know, we really believe that this is uncorrelated with these pre-war characteristics. So I hope that answers the question.
Great, thank you. Another question here, which has had lots of votes, is asking whether the wages also seem to include a workplace-specific labour supply shifter, and how this might impact interpretation when mapping the wage to productivities.
Yeah, so good question. Exactly as you saw. So one of the things we show in the paper, and you pointed out in the question, is that there are some sort of isomorphisms where different parameters enter together in the same way. There is that Frechet parameter that's a scale parameter for workers' commuting decisions. And inside the model, as the person asking the question mentioned, those conditional commuting probabilities, they don't just depend upon the wage, they also depend upon that Frechet scale parameter. And so there is an isomorphic combination that we call an adjusted wage in the paper that includes both the wage and that Frechet shape parameter. And so when you go to the data, that affects the interpretation of wages in the data in terms of the model. Because if you see variation in observed wages across locations, you know, if we could see the true wage in the model, we could just check the model's predictions against the data. But inside the model, the wage inside the model is going to include that adjusted productivity shifter. And so we sort of highlight that in the paper. We sort of, you know, show analytically that there are these sort of isomorphic combinations. That's also true for productivity and amenities. And I hinted at a bit in the lecture. That in particular expected utility is absorbed into the composite measure of amenities, and there's another isomorphism there. So yeah, again, great question.
Terrific. Maybe one more and then we'll stop for a break if that's all right for you. There's another question with lots of votes here asking about how far it's key here that the possible locations are fixed exogenously, and in particular whether the expression for expected utility would be sensitive to the chosen boundaries of the city if we were to add other areas.
So interesting question. So in the model, the value for expected utility will depend upon the set of locations in the city. So I guess the flavor of the question is whether this expected level of utility is endogenous to division itself, is the way I'm going to interpret the question. That's something we allow for in our quantitative analysis. So, implicit in the question, it could be that during the division period, West Berlin may become either more or less attractive relative to West Germany as a whole. And that could be for a variety of reasons. So for example, during division, there was an exemption where if you lived in West Berlin, you were exempt from military service. There were also some government subsidies for being in West Berlin. And so that's something that we explicitly allow for in our quantitative analysis. And so in particular, when we get to the structural estimation in the second half of the lecture, you'll see that all of our identification relies on relative comparisons between different parts of West Berlin. And so it doesn't really matter that this expected level of utility might change for reasons that are endogenous. That can be true. We can totally allow for it because that endogenous change in expected utility is differenced out when we difference between two locations within West Berlin. So the only thing we need is that the exemption from military service was common anywhere in West Berlin, which was true. Okay, and so it affects all of those locations equally. And so it differences out when we look at relative comparisons in different parts of the city. And so, if the division had been drawn in a different way, expected utility inside the city would be different. That would be true because it'd be reflected. The summations would be across different sets. But again, that wouldn't matter as long as when we do our econometrics, we look at relative comparisons between different parts of West Berlin. Because anything that determines the common level of utility for the West Berlin as a whole, such as how the exact boundaries were drawn, will kind of difference out when we do those relative comparisons. So it's kind of like a diff and diff interpretation.
Fantastic. Thank you very much indeed for such a fascinating first half. We want to leave plenty of time for the second half, so we will stop there on the questions and reconvene in 5 minutes at 12:20.
Great. Thank you very much, Claire. So I'm anticipating I'm probably not going to cover quite as much material as I thought. So just to sort of flag, I'm going to mainly focus on covering the Berlin paper because I don't want to rush. I want to kind of go into detail and tease out the analysis. And then I'll just briefly flag at the end some of the contributions of the London paper and do a little bit of advertising and maybe flag a couple of challenges for further research I think are really interesting in the quantitative urban literature. So let's pick off where we finished though. We saw what the model implied for the qualitative predictions of dividing Berlin. And then we've looked at the land price surface visually and we found some support for those qualitative predictions. And in the paper, we confirm with reduced form regressions that you also see further support for those qualitative predictions. And what I'm going to work towards now is how to quantify the model and structurally estimate agglomeration forces. I just flag one thing before we do, which is some of those placebos I mentioned. So we see these sharp negative effects of division here. So this is a decline in land prices between division and reunification, between the pre-war period and division, sharp nonlinear decline in land prices close to the pre-war CBD. So distance to the pre-war CBD is on the horizontal axis. An uptick in land prices close to the pre-war CBD following reunification. This third panel shows that most of the negative treatment effect of division is concentrated before 1966, as you'd expect, consistent with the rapid disintegration of economic links between East and West Berlin. And then these bottom two panels, this shows placebo, that there's no treatment in between 1928 and 1936. This shows another, that's this panel here. This shows another placebo. There's very little treatment effect between 1966 and 86. So there's no anticipation effect for reunification and there's no anticipation effect for division, consistent with identifying assumptions. So that relates to a couple of the questions that were asked earlier, just kind of showing these placebo checks and it looks like we pass those placebo checks. So the quantitative analysis of the model we do in 2 steps, leveraging this property of the model that I mentioned earlier, that it's recursive. And in particular, that recursive property means that just by estimating the model's commuting parameters alone, we can determine overall productivity and amenities. And that's actually pretty powerful because it means that those, in order to work out productivity and amenities, we don't have to make any assumptions about functional form of agglomeration economies, how strong agglomeration economies are, and we can already do some things quantitatively with the model. So we adopt that procedure, we make the minimal set of assumptions, show you what we can do with the model with those minimal assumptions, and so those conclusions are going to hold whatever your priors are about agglomeration forces. And then later on, we impose some extra assumptions, and that's what enables us to structurally identify the agglomeration forces. So how are we going to estimate the model's commuting parameters? Well, we're going to use the fact that although, as I mentioned earlier, a limitation of our Berlin data is we don't have a matrix of commuting flows between these 15,000 blocks, we do have some representative data from a survey of commuters for the post-reunification period. So we don't see the commuting between the many thousands of blocks, but we do see it between the 12 post-2001 districts of Berlin. And so what we do is we use those commuting survey data to estimate the model's commuting parameters. And so there are obviously a sort of couple of caveats about that. The model implies that the gravity equation for commuting holds at the block level, but in the modern 2000s commuting data, we only see those commuting flows between the districts of Berlin. So there's going to be a Jensen's inequality style correction term, because if gravity holds exactly at the block level, you think it couldn't also hold exactly at the district level because of Jensen's inequality. In the paper, we actually show empirically that Jensen's inequality correction is small in our application. And actually, David Weinstein and I have a paper on gravity in a trade context where we kind of show analytically why that is the case. You can actually solve analytically for what the Jensen's inequality correction term is in a log linear gravity equation model. So with that caveat, we're just going to use the model's predictions. The log commuting flow should depend upon a resonance fixed effect, a workplace fixed effect, and bilateral travel times, where we assume that commuting costs are affected by travel times exponentially. And so this is a semi-log specification, the log of commuting flows on the level of travel times. This coefficient nu here is actually a composite of two underlying parameters. The Frechet shape parameter, the elasticity of commuting flows to commuting costs, and the travel time parameter kappa that controls the elasticity of commuting costs to travel times. And so we're going to identify that composite parameter here. So we're just going to run this regression, estimate that composite parameter, and then using that composite parameter, we can actually recover wages to the power epsilon adjusted for that Frechet scale parameter somebody mentioned in an earlier lecture, in an earlier question. Okay, and so these wages here are defined to include those Frechet scale parameters and are raised to the power of that Frechet shape parameter. Once we get those wages, adjusted wages scaled by the Frechet shape parameter, we can recover overall productivity and amenities without making any assumptions about agglomeration forces. So what does that commuting gravity equation estimation look like? Well, as is common in the reduced form literature with commuting data, gravity equation fits the data really well. And that's why we wanted to build a model that featured a gravity equation, why we made these extreme value assumptions. We get an R squared using log bilateral commuting flows. All pairs have positive flows. So this is 12 by 12, 144 pairs between these 12 modern districts. We get an R squared of around 0.82. Because it's a commuting survey, some pairs have relatively few commuters. So we also do a robustness test where we drop the flows with few commuters. We find a very similar semi-elasticity of around 0.07. Final two columns are inspired by the trade literature, which is sort of argued in the presence of heteroscedasticity, you might want to estimate the gravity equation with a Poisson pseudo-maximum likelihood estimator. So we do that, we get very similar semi-elasticity. We also estimate it with the gamma pseudo-maximum likelihood estimator, again, a very similar elasticity. And so in conclusion, it looks like the commuting gravity equation is a pretty good approximation to the data that we have for the post-reunification period. And we're going to use this estimate here to estimate that composite parameter nu that combines the Frechet shape parameter and kappa, the elasticity of commuting costs to travel times. Just to show you visually that gravity is a good fit, in this top panel here, we show the log of commuting flows against the against the level of travel time in minutes after purging both of residence and workplace fixed effects. And as you can see, the linearity implied by the model doesn't do too much violence to the data. It looks pretty linear, which suggests that this semi-log specification is a reasonable approximation to the data. Once we've estimated that parameter nu, that composite parameter, as I said earlier, we can solve for those adjusted wages that I mentioned a moment ago. And then once we've got those adjusted wages, as we saw in an earlier slide, the model splits out a whole matrix of bilateral commuting flows between blocks. I can obviously aggregate that matrix and generate the model's predictions for commuting flows between districts. And that's what we show here in this middle panel here. I don't expect this fit to be perfect for a variety of reasons. Firstly, when we estimated this commuting gravity equations with our commuting flow data, we actually used the reported travel times in the commuting survey to be consistent, to always use commuting flows and travel times from the commuting survey. Whereas when we solve the model, we are using travel times that we compute based on solving least cost paths and allowing for the public transport network and the road network as means of travel between locations. And so if the commuting travel survey travel times are different from our model travel times, it won't be a perfect fit. It also won't be a perfect fit if gravity is not a perfect fit to the data. And of course, in practice, no model is a perfect fit to the data. Nonetheless, there's a strikingly strong positive correlation here as a kind of further sort of check on the model's predictions. The commuting estimation was only using travel survey data for 2006. But once we've got that parameter nu and we solve for wages, we can do that not only for the reunification period, we can do it for the division period and the pre-war period. And the model is going to spit out bilateral matrices of commuting flows between locations for the division and pre-war periods. We have some data on commuting patterns in division and the pre-war period. In particular, we have some data on the fraction of people that commute for different travel times. And so what we do in these bottom panels down here is we compare these models' predictions for the fraction of people that commute different travel times. So that's taking our entire matrix of bilateral commuting flows between blocks. We know how many people are flowing between the blocks. We know how many people are, we know the travel times between the blocks. And so we can construct inside the model a cumulative distribution function of the fraction of workers commuting different travel times. And then we also see those reported fractions in these survey data for the division period. And so we've just plotted the data cumulative distribution against the model cumulative distribution. Again, every model is an abstraction, but it looks like we're doing a reasonable job at capturing commuting behavior. And we do the same thing for the pre-war period. Again, it looks like the model is not doing too much violence to the data. And so these are sort of in the spirit of over-identification checks that our gravity assumptions don't seem to be doing too much violence to patterns of commuting flows in the data. So that sort of validates, again, using those commuting parameters to back out productivities and amenities, as I'm going to do so in a second. So in particular here, I'm going to show you some results using those. So once we've estimated nu, solved for our wages, and generated our commuting predictions, once we've got the wages, we can also solve, as I mentioned earlier, for the model's predictions for overall productivity and its predictions for overall amenities. And here I've done precisely that. And so I've got productivity before and after the division and before and after reunification. Same is true for amenities. And so one thing I can do is I can run some regressions of whether the changes in productivity implied by the model are correlated with division, and whether the changes in amenities implied by the model are correlated with division. And that's exactly what we do here. So we're just going to regress the log change in productivity or amenities between 1936 and 86 in these first two columns, and then between 86 and 2006 in the next two columns. I'm going to regress those on indicator variables for 250-meter grid cells for distance from the pre-war CBD. Okay, so it's a regression for West Berlin blocks, changes in productivities and amenities against distance from the pre-war CBD in East Berlin. And one thing you see very strikingly is division has a negative effect on productivity in locations close to the pre-war CBD, and it has a negative effect on amenities in locations close to the pre-war CBD. In comparison, reunification has a positive effect on both productivity and amenities. And that's some first suggestive evidence of agglomeration forces. Because the model would actually imply that productivity and amenities should change as a result of the city's division if there are these externalities in production and there are these externalities in amenities. because the parts of West Berlin close to the former pre-war CBD lose access to the dense concentrations of employment and residence there. Okay, and so this is sort of suggesting that the model says in order to match the data, productivity and amenities have to change in a way systematically correlated with division. And that suggests that it's consistent with the model's agglomeration forces. So first piece of evidence that a model without agglomeration forces is not going to match the data. Second piece of evidence, once we've recovered our productivities and amenities before and after division, inside of the model, we can use the model to do a counterfactual, assuming that productivity and amenities are exogenous. And obviously, as we discussed earlier, the model implies there are agglomeration forces, so in general, productivity and amenities won't be exogenous. But let's begin by assuming away those agglomeration forces, setting the agglomeration parameters to 0, and assuming that productivity and amenities are exogenous. Well, then in that special case of the model, we can actually do a counterfactual still for the effects of division, and we can solve for the model's predictions for the change in land prices in each location within West Berlin. And in fact, we show analytically in the paper, the model has a unique equilibrium in that case of exogenous productivity and amenities. And so we know that these counterfactuals are going to have determinate predictions for the impact of division and reunification on the organization of activity within the city. When we do those counterfactuals, we see a second piece of evidence that the model without agglomeration forces cannot explain the data. Okay, so why? Well, in particular, in that counterfactual, we see that the division of the city, assuming productivity and amenities to be exogenous, does reduce land prices close to the pre-war CBD. And so we get negative and statistically significant coefficients for division, and we get positive and statistically significant coefficients for reunification. So the model does imply some effect of division on the organization of economic activity within the city. And that's consistent with the model because the model says even if productivity and amenities are exogenous, the parts of West Berlin close to the pre-war CBD lose access to supplies of commuters and lose access to employment opportunities. And so we would expect land prices to fall in those locations. It is consistent with the model. But in particular, these treatment effects on the model's simulations, the model's counterfactual land prices, assuming productivity and amenities are exogenous, they're much smaller than if we ran these regressions using actual data on the change in land prices before and after division. And you saw those data on the change in land prices in those plots that I showed you earlier when I was discussing the placebos. And so that's a second piece of evidence that the model without agglomeration forces cannot match the observed very large changes in land prices that we see in the data close to the pre-war central business district in the parts of West Berlin near that central business district. And so the next thing we do in the paper is try to see, well, once we build in agglomeration forces, can the model explain the observed changes in land prices for a plausible set of agglomeration parameters? And that's the next thing we're going to do by structurally estimating the model's agglomeration parameters. Okay, so how are we going to do that? Well, there are going to be a sort of couple of features of our approach that are going to be important here. We've already seen how we can recover production fundamentals, the exogenous part of productivity in each location, little a. And we can recover residential fundamentals, the exogenous part of amenities in each location, little b. And in particular, the model has a very attractive property, which is that those exogenous components of productivity and amenities are one-to-one functions of the things we observe in the data, namely floor prices, workplace employment, residence employment, geographical land area and travel times, and the parameters of the model. And so if I tell you the parameters of the model and you see the observed data, you can just exactly invert the model to recover the implied values of these fundamentals that exactly rationalize the observed data as an equilibrium of the model. Why is that important? Well, it's important for two reasons. The first reason is it's going to enable us to construct moment conditions in terms of these fundamentals, because we've actually got a closed form solution for them in terms of the data and the parameters. So we can estimate the model's parameters using the generalized method of moments, rather than say simulated method of moments. We can use GMM because we actually have a closed form solution for the moment conditions. First reason it's important. Second reason it's important. Once we allow for non-zero agglomeration economies inside this model, it's inevitably going to have multiple equilibria, right? Because productivity in each location depends upon the density of surrounding employment density in all surrounding locations. If those agglomeration forces are strong enough relative to the differences in exogenous fundamentals across locations, generically the model is going to have multiple equilibria. And so you might think, well, doesn't that create an intractable estimation problem? How do you estimate a model with multiple equilibria? Okay, well, it seems like a big challenge. Well, the key thing that enables us to do it, that makes our whole approach tractable, is this one-to-one mapping. Because in particular, we're going to use the fact that we see an observed equilibrium in the data, and our entire estimation is going to be conditional on that observed equilibrium. Because conditional on that observed equilibrium, we can solve for these fundamentals and construct the moment conditions conditional on the observed equilibrium. So for our estimation, it doesn't matter that for the same parameters, there could have been another equilibrium that we didn't see. It doesn't matter, there could be many other equilibrium we didn't see, because all we need to estimate the parameters is the observed equilibrium, and we see that. And so it's kind of a very important feature of the approach, and that's used in a number of other, has been used since in a number of other quantitative urban models. So in particular, here are our solutions for the log change in production fundamentals and residential fundamentals before and after division. As I highlighted earlier, they're sort of composites of a couple of different parameters that enter the model isomorphically, and that's why they've got a tilde over them. And then on the right-hand side, we've got things we observe in the data, like floor prices, wages, adjusted wages that we can recover from the data, and these are the production externalities that are functions of observed employment densities and travel times. And again, same for residential fundamentals. On the right-hand side, everything is data, functions of data, or parameters. To estimate the model, we're going to take some parameters from central values in the literature, like the share of residential land in consumer expenditure, the share of commercial land in production costs, and then we're going to structurally estimate the agglomeration parameters. How important are production externalities, lambda? How rapidly do they decay with travel time? How important are residential externalities, eta? How rapidly do they decay in travel times? And then we're going to again recover this composite commuting parameter, and we'll also recover the Fréchet shape parameter. What are the moment conditions? Well, the moment conditions are, we're going to use the assumption that the change in the exogenous part of productivity, the production fundamentals, and the change in the exogenous part of amenities, the residential fundamentals, are uncorrelated with the exogenous shock of division. Okay, so in particular, we're going to assume that these log changes in production and residential fundamentals are uncorrelated with indicator variables for distance grid cells to the pre-war CBD. So what is this identifying assumption doing? It's saying we know the change in the organization of economic activity inside the city in West Berlin was correlated with division. It's correlated with distance from the pre-war CBD. We've already seen that earlier for land prices. And we saw it earlier for overall productivity and amenities. We know overall productivity and amenities are correlated with division, with distance from the pre-war CBD. But the identifying assumption here is that the exogenous component of those is uncorrelated. And so what this is doing is it's estimating the agglomeration parameters. It's choosing those parameters such that they make the change in fundamentals, production fundamentals and residential fundamentals, uncorrelated with those distance grid cells, flat across different parts of West Berlin. So we're finding values of the agglomeration parameters for which the entire of the systematic organization of economic activity within the city is driven by the model's agglomeration forces. Why do we think that's a valid identifying assumption? Well, because before the Second World War, no one was anticipating Berlin to be divided in this way, and the division was driven by these exogenous military and strategic considerations. And so we think that the division of the city was not correlated with the fundamentals in these individual parts of West Berlin. And then we have a couple of other moments that help pin down the commuting parameters, which rely on the fraction of workers commuting different travel times and the dispersion of wages. What do we find? It's pretty interesting. Firstly, the commuting travel time semi-elasticity, that composite parameter. The parameter we estimate here in our structural estimation is actually pretty similar with what we got earlier when we just ran a gravity equation on the commuting flow data for the post-reunification period. So that's another kind of nice check. We can now separately identify the Fréchet shape parameter. That comes out around 7, which is sort of roughly comparable with the Fréchet shapes people estimate in the trade literature, which Eaton Quantum get around 8 in the trade literature. And it's roughly comparable to what we estimate in a different setting in the London paper, where we get a Fréchet shape parameter of around 6. And it's sort of broadly in line with a few other studies as well. In terms of agglomeration externalities in production, we have an elasticity of productivity density of around 0.07, which is a bit on the high side compared to the existing literature across cities. So at the upper end of the range tends to be between 3 and 7, so we're kind of at the top of that range. But the other thing we see is that these production externalities decay rapidly in travel times, very high exponential decay parameters. And so although production externalities are strong, they decay rapidly within the city. And so city level production agglomeration economies are sort of lower than would be implied by this block level elasticity because they decay in travel times. And that rapid decay in travel times is also consistent with other estimates. For example, Azagi and Henderson also find rapid decays in production externalities. Another very interesting finding, as I mentioned earlier, we find pretty strong externalities in residential decisions. In fact, they're stronger than for production externalities. And again, they decay very rapidly in travel times. And I think this is a kind of very interesting area of research at the moment, micro-founding and digging deeper what is driving these externalities in residential decisions, as that relates, for example, to Milena Almagro's recent job market paper this year. We estimate the parameters both just looking at division, looking at reunification, and combining the two experiments. We find pretty consistent pattern of estimates across those 3 different experiments. This kind of shows you just how localized these production externalities are. Within around 10 minutes travel time, they basically go to 0. So 10 minutes travel time is, walking around a kilometer. Going around less than a kilometer by underground and railway lines, and it's a little bit further if you actually walk. All the way around. It's about a kilometer by walking, and I think it's about 3 kilometers traveling by underground and suburban railway lines. Sorry, I'm getting tired. But these production externalities decay rapidly in travel time. Same is true for residential externalities. In contrast, utility falls much less commuting, and that's consistent with the fact that people are commuting quite substantial distances, and commuting up to around 45 minutes travel time. Then the final thing we do in the paper is we do some counterfactuals for the estimated value of agglomeration forces. And what we show here is that once you use the model's estimated agglomeration forces, it is indeed quantitatively successful in terms of explaining the observed reallocation of economic activity within the city. So we get counterfactual changes in floor prices roughly of the same magnitude of the treatment effects that we estimate if we run these regressions using the actual observed data. And so the model is quantitatively successful in terms of explaining the magnitude for the estimated parameters. Notice, again, there's a caveat here. Once you have agglomeration forces, the model potentially has multiple equilibria. The equilibrium selection rule we use is we solve for a counterfactual equilibrium using the initial values from the observed equilibrium before division or the observed equilibrium before reunification, and then kind of using those initial values to update to solve for the new equilibrium. So implicitly, we're solving for the closest equilibrium to the equilibrium before division or reunification. And then we sort of show in the other columns how the magnitude of the treatments varies if we switch off agglomeration forces in production, switch off agglomeration forces in residence, etc. And so that sort of concludes the first paper I wanted to cover today. And what is the punchline? Well, we develop a quantitative model of urban structure to estimate agglomeration forces. We show how the model exactly rationalizes the observed data. We show that we can use it to structurally estimate agglomeration forces. We find substantial agglomeration forces roughly comparable to other estimates. Couple of interesting findings, very, very localized within the city. Another interesting finding, agglomeration forces for residential decisions, if anything, even stronger than for production decisions. And then the model is quantitatively successful in terms of explaining the reorganization of economic activity within West Berlin. And not only is it successful for the targeted moments, but it also does a good job on a couple of over-identification tests. In particular, we showed some over-ID tests on commuting patterns, and we also show some other ones in the paper using information on the ratio of floor space to ground area, where the model's predictions seem to be confirmed against some separate data that we have on floor space to ground area. I need to stop in a couple of minutes. So what I'm just going to do briefly is just flag or do a bit of advertising for the paper on London, and then make a kind of more general point about these quantitative urban models. So as I mentioned earlier, the London paper looks at a very different experiment. It looks at how cities reorganize in response to transport improvements. So I sort of recommend that paper for those of you interested in transport improvements. Also makes a couple of methodological improvements. over what we did in the Berlin paper. In particular, we developed an approach that holds in a whole class of models. So not just the canonical urban model that I've just looked at today, but also new economic geography models with differentiated varieties like Help and Krugman, Eaton-Corton models with many goods and trade costs, Armington models with differentiation by location. We develop a sort of methodology that holds in an entire class of models. And in particular, the reason we're able to do that is we have this bilateral matrix of commuting flows that we actually observe in the data. And so we develop an entirely different structural estimation methodology that uses that matrix of bilateral flows. And it's because we've got that matrix that we can encompass the class of models in a way that was not possible in the application in Berlin when we didn't see the bilateral commuting data. So one general sort of conceptual point I want to make about the London paper, and this is sort of something that I'm sort of keen on pushing, is one thing we do is we sort of show that the revolution in transport technologies from the invention of the steam railway explains something that we see very strongly in the data in London, which is that you see the residential population in the center of the city collapsing after the railway network is built in the mid-19th century. And you see employment during the day rocketing in the most central parts of the city. That's very natural in these, has a very natural explanation in these quantitative urban models, which is that the reduction in commuting costs is enable you to separate where people live and where they work. So locations that are good for production, like the central parts of London, can specialize as a workplace location, and whereas the suburbs, which are attractive places for residents, can specialize as a residential location. And the thing I wanted to flag here is one of the things we really sort of push in the paper is sort of again showing that the model can do quite a good job at matching the patterns we see in the data. So you see here, the dashed line here is actually the model's predictions for workplace employment in the part of the central of London. And then again, we also report some over ID checks where we show that the model going back in time can explain the change in commuting patterns. So this is showing some data on commuting patterns around the turn of the 20th century. Black is what's in the data, gray is what is in the model, and it's showing the fraction of people commuting different distances. The model is doing a reasonable job. And then again, if we go back earlier in time to the mid-19th century, in both the model and the data, most people live very close to where they commute. Most people live close to where they work, and we had this very primitive commuting technology before in the very, very early days of the invention of the steam railway. But I should stop there to leave some time for questions. And so this is just to sort of advertise that second paper, looks at the impact of a transport improvement and shows that these models can really imply that these large-scale transport improvements can lead to quite substantial changes in the organization of economic activity within cities. And the final thing we do in that paper is sort of use the model to do a cost-benefit analysis of the construction of the 19th century railway network. And we show that the sort of net present value of the increase in land and buildings substantially exceeds estimates of construction costs of that transport network. But I should stop there to leave some time for questions, and sorry for sort of running over a couple of minutes, Claire.
That's fantastic. Thank you very much indeed. So there have been a huge number of questions here. Daniel's been answering some of them in the box, but a few here still for you. So there's a question here about how we should think about durable structures, given the structure supply function and the decline in population following the war.
Yeah, that's a good question. One of the things we were careful of in the Berlin model is, as I was discussing earlier, we allow for this sort of density of development for every location that's backed out from the implied observed data. And in particular, when we did our structural estimation, we only specify the moment conditions in terms of production fundamentals and residential fundamentals. We do not include any changes in the density of development. And that's for a good reason, because if you think there's an upward sloping supply function or buildings may decay in response to declines in demand for floor space, you would actually expect, even in the absence of agglomeration forces, you'd expect the density of development to respond endogenously to changes in the demand for floor space. And so if, in the spirit of the question, if buildings were there, they didn't immediately decay, but they may have decayed gradually, and the gradual rate of decay would have depended on changes in the demand for floor space. The model allows that because we just let the density of development adjust flexibly to fit what is implied by the demand for floor space inside of the model. And we don't use that information at all in any of our orthogonality conditions. Again, as a little bit of an advertisement for the London paper, in the London paper, we actually develop a explicitly dynamic model where we actually allow for the possibility that agents can make forward-looking investments in building capital. that are subject to adjustment costs. And the structural estimation methodology we used in that paper is actually consistent with that dynamic model. In fact, it's nested within the class of models for which that structural estimation procedure holds. And so you can also impose more structure on those forward-looking investments. Although in the Berlin paper, we just backed them out and applied it by the changes in demand for commercial and residential floor space.
Great, thank you. So the next question here is asking whether you could talk a bit about your assumptions in the context of the literature showing wasteful commuting. So i.e. that commutes are often longer than what a simulation of location choices would suggest. Great question.
So great question. And in fact, that connects with the bigger question, which is sort of the efficiency of the equilibrium and the extent to which there is too little versus too much agglomeration. So those are really fascinating questions. There are actually several sources of market failure in the model here. In particular, there are externalities in both production and residential decisions. So generically, in general, location decisions are not going to be efficient. A further kind of externality which we don't take account of in the model is potentially through congestion in commuting. In particular, the way we model commuting costs is we just model them as a constant elasticity of travel time, as I was mentioning. But a further source of externality, which is directly related to the question, could be congestion in commuting decisions. And in terms of wasteful commuting, I mean, that's a very pejorative term, the way it's used in the literature. The way I'm going to interpret it is in the kind of narrow neoclassical economics sense, which would be whether the commuting decisions of the workers would coincide with the decisions of the social planner. And that question would depend not only on the externalities in commuting through congestion effects, it would also depend on all the other externalities in the model, in particular on production externalities and residential externalities. And for anyone who's interested in that, I wanted to kind of advertise that Pablo Fagelbaum and Cecile Galbert have a very, very nice paper that looks into kind of optimal policies in the presence of these externalities. It's a different model, so the setup is slightly different, but it's again within these group of quantitative spatial models. And so I kind of recommend also looking at that model. In some of the literature on wasteful commuting, I think some of the literature is there also more connected to kind of behavioral type theories where individuals may not be making rational optimizing decisions. That's something that I don't really feel fully qualified to speak to, although I do know there is a kind of a large literature on the behavioral issues there. But even within the kind of neoclassical setting, I think there are lots of kind of interesting questions here about the efficiency of the equilibrium and what the planner's decisions for commuting behavior would look like. So really interesting question.
Fantastic, thank you. So the next question here is asking about this assumption that there's a fixed common utility level, which we might justify through free mobility between West Berlin and the rest of West Germany. So given this, the question is asking an implication of the division would be that the total population in West Berlin falls during division and rises again after reunification. And is this something that you pick up in the data?
Yeah, so great question. When we do the structural estimation, we're really careful only to use variation across different locations within West Berlin. So only to use those relative comparisons across different parts of West Berlin. And that was for the reasons we were discussing earlier in the earlier questions, namely, we think that expected utility may have changed in systematic ways during division because, for example, of exemptions from military service. And so we don't want to use that variation in our identification. We only want to focus on relative comparisons within West Berlin, which weren't affected by those other policies. But it's exactly right that the model does generate this prediction that the total population of West Berlin should fall. And that's indeed true in the counterfactuals I was showing at the end. The population of West Berlin does decline substantially as a result of division. We don't actually do an explicit comparison of the overall decline in the model for the population of West Berlin to the overall decline in the data. And that's because of the existence of these other policies like the military exemption and subsidies to firms that located in West Berlin, because those other policies are not in the model. And so we wouldn't necessarily expect the model to be exactly match the overall decline of West Berlin in the data. So again, that's like a kind of diff in diff point. There are other things happening to the pure time series change in West Berlin, we don't want to use that to identify the model's parameters. We only want to use the relative comparisons across locations within West Berlin. And that's why the quantitative decline in overall West Berlin population in the model need not be the same as in the data. But it's definitely true that it does generate a substantial decline, as we also see in the data.
Great, thank you. So another question coming up here is, how far can we think of epsilon as a deep parameter here? So the question's phrased very long, but I see we've got 1 minute, so I'm going to stop there and let you speak rather than me.
I'll try to be quick. So it's a good question. In defense of it, we would sort of argue that the log linear gravity equation does fit the data pretty well, and that's what you need. You need a common Frechet shape parameter in order to preserve a log linear gravity equation. There are definitely very interesting recent papers that are generalizing this to have multiple groups which have different Frechet parameters, and then endogenously in the gravity equation, the overall slope in that overall gravity will be a composition weighted average of the constant slopes for the individual groups. So I definitely think there's scope to enrich these models by having heterogeneity and potentially some compositional effects. Very interesting. But to a first approximation, log linear gravity with a single group does a great job at fitting the overall data. We find that in both our papers, and it seems a pretty robust feature in other studies. So we think it's a good approximation, but obviously you can enrich the model and look at other questions by building in multiple groups. I think I should stop there to stay on time.
Fantastic, thank you very much. Hand it back to Daniel.
Thank you much, Steve, for this fantastic lecture. It is a long paper. That was really useful. Thank you very much to all of you for sticking with us for another really packed lecture, and I look forward to seeing you next week for our next lecture. With that, good night from London.